Okay, so welcome everyone to the spring term and the New Technologies in Mathematics seminar series. So this semester we'll be having more of a focus on AI and theorem proving, as you know, if you saw my talk at the CMSA last February, or from many other places, that interactive theorem proving is becoming a more and more interesting and potentially valuable tool for mathematicians. And if we could combine it with AI, that would perhaps be the most revolutionary of the many technologies that we've talked about for how people actually do mathematics. And we're fortunate to have Josef Urban give us an introduction to it. So Josef is one of the leaders in this field. He's a PI in two major collaborations in Europe of the subject, and he's also the founder of the leading conference in the field, which is also called the AITP. And so we are delighted to invite you to speak.
Thanks, Michael. It's an honor to be at your seminar. And this is, as usual with my talks, untested. And I want to give you quite a few demos. So let's see how it goes. Let's get into it. This is the ambitious overview, so I will quickly do some motivation. I will not go too much into formal math because Mike said that you will have more deeper introductions into formal math. And I will mostly focus on the various ways how we combine typically some machine learning and some theorem proving tools, and what it can be divided into is sort of high-level reasoning guidance called premise selection, and that relates to tools called hammers that are really used, especially in the Isabelle system, quite a bit. Then low-level guidance of theorem provers, where you really guide possibly very fast theorem prover by a machine learner. You are guiding the inferences of those systems by hopefully fast machine learning tools. And then something in the middle that I call the mid-level reasoning guidance, which is, for example, guiding of the tactical theorem proving systems like, let's say, Hall and Koch, where it makes a lot of sense to focus on that level. And I will mention some, I will try to mention some sort of interesting stuff going on with neural networks, such as using neural networks for guiding and especially synthesis and conjecturing. And I will try to say something about automated formalization. So basically using something like linguistic machine translation to translate informal mathematics to formal mathematics, where we can sort of play the automated reasoning game. So this is my very high level introduction, which is the sort of most ambitious motivation is that we would like to sort of somehow automate what mathematicians and scientists are doing. And we sort of know that that includes all sorts of inductive reasoning, like analogizing, induction from examples, pattern matching. But we also know that, especially in mathematics and other hard sciences, deductive reasoning and really finishing your proofs is important, and there are all these feedback loops between that. So between these two sides of what we call thinking, I guess, and we would basically try to experiment with that on computers. So long ago I have decided that formal mathematics is a really nice playground for doing that, because you have a lot of data, you have a lot of corpora and knowledge from which you can learn by all sorts of machine learning methods. but you can also really do deduction. You can see when something is proved. You can, and because these systems are very secure, exactly for the need of the secure verification of the proofs, you know that when you find a very unusual proof, it's typically still a proof unless you have a bug in your system, which really doesn't happen too much. So it allows you to do a lot of deductive or learning guiding deductive exploration, and we don't know where it takes us, but it's a cool cool area to experiment with, and hopefully to sort of develop systems that help mathematicians and I don't know, computer scientists, etc., with their reasoning or their tasks. So for formal,
I had a quick question. When
Yep.
you meant synthesis, do you mean like a program synthesis?
So yeah, that's
If
a good.
it's better for you to answer later, it's fine. I just wanted to ask.
It's you can think of it as program synthesis. So I will give some examples where, for example, you have a set and you want to find the Diophantine equation that characterizes that set, or you have a lambda expression and you want to find a combinator expression that results in that lambda expression. So
Okay.
you could in my general comment on the relation between, let's say, programming and algorithms and mathematics and reasoning is that reasoning is bigger, programming is more specialized but also more industrially important, and the people who do reasoning quite often consider programming like a special part of reasoning. For example, Henk Barendrecht, who is one of the big guys in Nijmegen, working at some point with type theory and Coq system and lambda calculus, likes to think about Coq as the combinations of the sort of algorithmic part and the reasoning part, where the sort of algorithmic part is sort of automated and the reasoning part is the human input. But for me, as more of the reasoning guy, I would say that the tasks we are trying to solve are sort of superset of the tasks that the programming people are solving. But obviously, that's my point of view. Like they might have the other point of view.
Got it. Thank you.
So formal math, as I said, I will not go deep into it, but probably many of you know that there is this succession of people like Leibniz, Frege, Russell, Hilbert, Gödel, Church, who basically came with putting math on formal logic foundations, which, by the way, also led to the rise of computers. And that, in my opinion, that's really one of the biggest things that happened in the last century, and we are still reaping the benefits. And for example, what I'm doing is really heavily relying on the fact that mathematics has been formally embedded into logic, and we can really play with mathematics like with a computer game today. So formal math is exactly this. People took this seriously in, let's say, 50s or more like 60s. These people like De Bruijn, Milner, Triboulet, Boyer and Moore, Mike Gordon, Gerard Ie, Larry Paulson, and they created all these systems like Automath, LCF, Mizar, NQSum, ACL2, HOL, Coq, Isabelle, etc., where they really tried to formalize mathematics, and they really progressed. So in the beginning, or let's say in the last decade or two, there have been really large verification projects like the FlySpec project, the verification of the formal proof of the Kepler conjecture, the four-color theorem, the odd-order theorem. So verification of all sorts of industrially important projects like verification of compilers, of operating system microkernels. So it's really becoming more and more real, more and more usable, both for mathematicians and for industry, basically. And the formal math, like this is, I think, borrowed from Tom Hales's talk at the Bourbaki seminar, is really conceptually very simple. So you write your axioms and theorems in a sort of parsable, computer understandable way, like basically you invent a programming language for that. And you define your inferences, and then you just use the computer that your proofs follow the rules, the inference rules. So it looks really simple, but it's not simple in practice because of the cognitive gap between how computers work and how human mathematicians work. So one guy called it the high temperature and low temperature. So the I would say that a lot of what was happening in the formalization field was going from the low temperature to something that allows you to do more steps or bigger steps in one command, for example. So that's the sort of tactical theorem proving. For AI and theorem proving, like I have this long talk at AGI 18, which you can click on. So there is a lot of interesting history and also tension between like the intuition-based people and the formally oriented people. So I always have this picture from Logicomics where Poincaré argues with Hilbert. And like there is this tension between them where one doesn't like formalism and the other one believes that it's the future. And basically Turing is a very interesting guy because in his he proved the undecidability, right? Like he defined the halting problem, etc. But he also, like in the 1950s, he basically invented artificial intelligence, or started artificial intelligence. And in his 1950 paper on the Turing test and the computing intelligence, he basically ends the paper with speculation about learning machines, like how would you train a computer to play chess. So it's sort of a very visionary, and it goes really in the AI direction a lot. And we were just talking with Mike Douglas about Pat Langley working on the Kepler laws. So there is Doug Lenat's work on the automated mathematician and Eurisco. So these are things that were happening, I think, in the 70s and 80s, where people were coming up with various sort of symbolic approaches to do AI for science, basically. What sort of started the field in which I am sort of working, at least for me, is this work in the late 90s by a group in Munich, Jörg Denzinger and Stefan Schulz and other people. And they really started to explore machine learning for automated theorem proving. Like they had this paper or technical report learning from previous proof experience. And that's really very interesting reading even today. Like they suggest many things there. In my long ago master thesis, I was very ambitious, and I was trying to use inductive logic programming, this ILP, to basically learn explainable rules and programs and heuristics from large mathematical formalization. And that was really an attempt that was doomed to fail for all sorts of reasons, but it also gave me a lot of, I would say, insight or feedback, like what needs to be done. And I would say that since something like 2000, we have started to use these large formal or big proof corpora based on these systems like Mizar, Isabel, and Hall and Koch to play the game, to do various machine learning and theorem proving in these large libraries and to combine the two things. And I wanted to also mention, like, for many, especially newer people, AI, typically there is a confusion between what is AI, what is machine learning, and what is deep learning. So for some people, AI means deep learning today. So if you want to get more into it, I recommend this Ben Goertzel's talk. Ben Goertzel is one of the fathers of the artificial general intelligence conference, and he makes nice explanations in the talk. So the big AI visions are the one side of that, like we would like to automate, verify math and science, etc. And the other side of this is that what we are doing is practically useful, like systems like hammers or tactically guided theorem provers are today really used by the verification people. This is one slight overview of what we are sort of doing today. So like I mentioned, there is various levels on which we can do things. So like I said, the most established and I would say easy on the engineering side thing to do is to, when you have a big corpus and you cannot feed it all to automated theorem provers, to basically use some machine learning from the proofs that you already know, and typically there are many proofs in the corpus, to pre-select the lemmas for your next proof attempt. So that's called premise selection, and it's been explored quite a bit in the past, I would say, 15 years, and it's a established component of the hammer systems today. You can also, on this very high level, use machine learning to decide which automated theorem proving strategy or automated theorem prover to use, or which portfolio of strategies. So people have done machine learning for that sort of thing too. You can also select something called hints, which is a very good weapon for solving some especially algebraic problems by automated theorem provers. So that's not done so much, but it's a very similar task as the premise selection. Instead of choosing directly the axioms, you are choosing what knowledge will be guiding the proof search through sort of the hints mechanism. And I will not go into it too much in this talk. Then there is the low-level guidance. So that's really interesting, and I have been focusing, and my group has been focusing on that, let's say, in the past 4 years quite a lot. And I think there are really very significant breakthroughs. So some 5 years ago, we couldn't improve we couldn't improve too much, neither like the sort of vanilla simple systems, and we couldn't improve too much the best automated theorem provers. And the situation changed about 2 years ago, 1 or 2 years ago, when we really basically did a breakthrough by putting very fast but very good machine learning into it, and it suddenly started to work. And it's in my opinion a turning point where even the biggest opponents of machine learning in the automated theorem proving community basically have to agree that the machine learning is beating them today. And you can also guide crazy on a crazy low level, like guiding the kernel steps in these tactical interactive theorem provers that are called also LCF style theorem provers. And some people have tried it, but that seems to be really too ambitious for all methods today. And the very reasonable thing to do, like I said, is this guiding of applications of tactics in the tactical theorem provers. So that's probably like, at least in some cases, these systems are today beating the hammer systems. And you can do inventions of ATP strategies for classes of problems and conjectures and suitable concepts and models. You can do theory exploration, which means basically developing conjectures and theories by all sorts of inductive and deductive methods. The very cool thing that you can do is to switch between proving and learning. So it's been like this learning/proving loop has been very productive. I'll show you some data about it. And there's this autoformalization when you basically try to take a piece of Latex and translate it to formal math. And again, you can do it by machine learning and assisted by technologies such as type checking and theorem proving or disproving, etc. So this is sort of the spectrum, at least to some level. There are many corpora today. Like some of them have been translated to like the standard automated theorem proving formats for a long time. Some of them are. It took longer to translate them. For example, COC is pretty challenging to translate to, for example, first order logic, so that it gives you something, so that it's not unsound and incomplete, or unsound and incomplete too much. But basically, there are really many benchmarks, and you don't need to translate things down to some standard automated theorem proving format anymore today. You can really also, people do it, play the game in the native logic of the theorem prover, like with these tactical automated theorem provers. And obviously on this last line, there are also all these informal or semi-formal corpora, like this proof wiki, which is informal, but sort of with some quite rigorous structure, the same for stacks, for example. So stacks is much more controlled than archive, for example. So again, you can sort of do various experiments, typically involving formalization, but also just some machine learning and recommendation on these corpora. Demos. Okay. So what should we start with? I'll show you the latest. Just see how I'm doing on time. Oops. Okay, I should go fast. So we have been now for about half a year running a big evaluation on the Mizar library, which has something like, I'll show you the top of this GitHub page, which is something like 58,000 top-level problems. And basically, we are doing the hammering stuff. So we are trying to use automated theorem provers guided by machine learning, together with training premise selection, which chooses the relevant premises from the big corpus, to prove as many of them as possible. And some of them are really long, like some of them have like hundreds, or some of them might have even like 1,000 of lines. And in 2013 or 14, with Cezary Kališík, we could prove about 40% of them with the premise selection, and 56% of them when we used the human advice for the premise selection. So we basically took advice from the proof that was already written in the Mizar library, and we just wanted to sort of replay that proof by the automated theorem prover. So this last evaluation, like we started using a learning version of eProver called Enigma that uses like gradient boosted trees and graph neural networks. And we are basically running this proving and learning loop in various ways, both for the premise selection and for the internal guidance of the automated prover, of the eProver. So you can see sort of how the progress goes. So currently the total of theorems we can prove is something like 73.5%. And what I wanted to show you is this, how do I, yeah, am I there? I might need to do it again. Search for Pita. Okay, yeah. Oh, so this is the Pythagoras theorem. So you have real unitary space that's some, well, you can imagine vector space with scalar product, inner product, dot product, whatever you call it. And oh, maybe I'll click on this. So yeah, here everything is linked. So you have 2 points or vectors in that space that are orthogonal, and now you basically state the Pythagoras theorem. So if you take their sum, and the norm squared equals the norm of x plus norm of y squared, right? And this is the sort of declarative Mizar proof, which refers to various theorems in the library, and like the definition of orthogonality, like x and y are orthogonal if their scalar product equals 0, right? Or x plus y, scalar product x plus y is greater or equal to 0 because of the definition of scalar product, etc., etc. So you somehow draw these theorems and definitions from the library, and in some 15 lines you finish this proof. And we, for a long time, this was too hard for our automated technology, but finally in May we got this proof. So this is the statistics of the proof. So it has 180 inference steps, like these clause steps. Initially, the proof contained 342 formulas, axioms from the big Mizar library, which has something like 100,000 statements in it. The proofs are generated something like 65,000 of new facts, new clauses. And all these clauses are ranked by the machine learner as they are generated, as you sort of infer between the axioms and the generated facts. You basically score or rank all of them either by the gradient boosted trees, or which was the case here, or by the graph neural networks that we have inside Enigma. And based on that, you select so-called given clause or processed clause, which are used for doing inferences with the previously selected clauses. So that's a so-called given clause algorithm, which is like basically the strongest paradigm for automated theorem proving today. So you can see that of the, let's say, 61,000 non-trivial generated clauses, we have selected something like 4,000 clauses for doing the inferences using the trained guidance. And the guidance at this point was trained on something like 500,000 proofs that were generated initially just by running untrained eProver, which gave us something like 15,000 proofs, then training the guidance, and then solving more and more problems, and also solving the old ones more efficiently, and getting more and more proofs, and learning from them over and over. So that's how we got to this thing that we couldn't prove before. Here is Yep.
Yeah, because you say, well, that's right, you're showing us, but the training set is produced by some sort of free generation of proofs, or it was based on some corpus, or where did the training set come from?
Oh, the training set starts at 0, so you just have 60,000 problems, and you run them over with an untrained theorem prover. So whatever is the state of the art in automated theorem proving without machine learning, you just run untrained e-prover with its best strategies, and it gives you something. So in 10 seconds, it may give you something like 50.
It has an ability to prove, and that was the starting point for the guidance. And then you're giving it these Mizar statements of lemmas, just totally exactly the form they appear in the library.
Oh no, you need a translation. So from that nicely looking stuff which I was showing you and which is almost readable, you translate to TPTP, which is this stuff.
Okay. So
which,
you're giving,
and that can be read by the automated theorem.
Okay, so you're giving it that because it's okay.
Yeah. So I wanted to show you one more. So there is a probably oversimplified version of Carmichael's theorem about Fibonacci numbers in the Mizar library, which is like one of the last theorems in that article, and it has a long proof. So the proof is something like 120 lines and involves some limiting argument and some induction argument. And so basically what it says that if you have 2 primes, m and n, and m divides fib n, like the nth Fibonacci number, then if you have an r that is smaller than n, then m doesn't divide fib r, so fib r. So basically, if you take any sort of smaller Fibonacci number, then m will not divide this. And this seems so there is a theorem called Carmichael's theorem, which is more complicated, and it seems that the Mizar people sort of simplified it so that they could prove it more easily, but they probably oversimplified it. And they told me that they followed a proof written by some mathematician. So this is not their product. This is their formalization of somebody else's product. But what happened quite recently is that basically the trained machine learner found a much simpler proof based on a lemma, which was, by the way, solved by Bob Soloway when he was struggling with learning Mizar, which says that Fibonacci m GCD Fibonacci n is Fibonacci m GCD n. So this is quite an easy lemma to prove, and you can really go very quickly for that lemma with the primality as assumptions to show what these Mizar people were trying to show in a very long proof.
That lemma was in the library, and it decided to choose it as one of the
yeah.
Okay.
Yeah. So this is a game that we have been playing very long. Like it happened to me first time in my PhD thesis like 15 years ago, actually. But you really, when you talk about some human level intelligence, like my first observation is that what the premise selectors do, and it's irrelevant whether you use simple machine learning or complicated machine learning, they universally do things differently than humans. They see wider, and they can do these things much more easily. We have done it on the flyspec corpus. We have done it on the Mizar corpus. We have done it on the Isabelle corpus. So it's some sort of evidence that what we are doing will not be totally similar to humans. Basically, it will do some things better and some things worse. I think I'm sort of pretty low on time,
Well, these
maybe I'll show
demonstrations
you.
are a good way, I think, of showing the state of things. Perhaps we can see another one.
Okay, I'll show you some more then.
Yeah.
This is a Mizar hammer. So the hammer has been popularized by Larry Paulson and Isabel, but I have created the Mizar hammer, so I did this video a long time ago, so I will show it to you. So this is a Mizar proof saying that if a set X is a subset of cardinal M, then the cardinality X is also a subset of the cardinal M. And the Mizar proof checks, it's been written by a human. And now I'm basically removing the references that were supplied by the human to make the justifications of the steps in the proof. And I'm asking the hammer. And the hammer is sitting somewhere on my server in the Netherlands at the time and doing the premise selection from the big library by using all sorts of machine learning on the library and using the trained models and running the automated theorem provers like Vampire and eProver on that. And it's sort of coming back with the replies. So you can see that the replies are quite different from what the human put there. But once the hammer comes back with that reply, you sort of know that this is something that you can use. So you can sort of post-process it. You can prune the proof, but it basically, to some extent, it works as some verified advisor in the sense that what it tells you is not incorrect. It's not just some sort of machine learning advice, but it's a verified proof that it is proposing you. So especially in Isabel, this sort of mode of work when you are calling the hammer in the background is really very popular today. So this is the hammer demo. And I'll show you Thibault Gautier's tactic-toe. So that's a system. It's the first and so for a long time the only working really usable system doing tactical guidance of tactical provers or learning-based guidance of theorem provers. So what he's doing is he's calling this TTT tactic on the goal that he supplied. And it has loaded 12,000 tactics and 3,000 theorems, and it has pre-learned on them, so it knows at this point on which goals how to apply which tactics during sort of the tactical proof search, and it's doing some sort of Monte Carlo style search when it transforms the original goal by a tactic, by the most likely or relevant tactic into another goal or list of goals. And then it sort of goes deeper and further tries to basically discharge those goals by other tactics. That's a system that, as I said, can basically beat the hammer. Its performance is beating the hammer for a whole 4, which has, by the way, been also done by Thibault. And one of the reasons for that is that the hammers are not very good at high order reasoning like induction. Whereas what these tactical guiding systems are doing is to some extent cheating, in the sense that they take whatever algorithms, whatever tactical methods and procedures that can be quite complicated programs are already present in the library. And there is quite a few of them because the formalizers program them in order to be efficient. So when somebody like John Harrison programs a tactic called induct, you can bet that that induct tactic is very well tuned and designed for the tasks in the library. So So in some sense, it's not a big wonder that the sort of tactical guidance works better than sort of a vanilla automated theorem prover, that even if it was complete for the task, if it theoretically could be able to prove the task, it wasn't sort of too much designed for that particular task. So that's also why it really makes a lot of sense to sort of do this mid-level guidance for, especially for the tactical systems. And people have done it for other systems. So I'll show you another one for Coq that's quite recent by Lasse Blaubruck. So it's very similar in some sense to tactic, though it also basically grows tactical proofs. So here he can basically suggest suitable lemmas for the goal that he's proving, and then it will just tell him what he can use. But in this case, there is nothing in the database. So he does the proof by himself. And as he does the proof, when he gets to the second goal, there is already something in the database. So when he will call suggest here, it will suggest something useful. You can see the ranking of the tactics that he can use here. And when he says search, it will actually finish the tactical proof for him. So here you can see the tactical proof. So this has been now done. I think the Google people have done it for whole light. I think that there are people thinking about doing it for lean, etc. So it's a thing that makes a lot of sense for the tactical theorem provers. This is the last demo showing you some sort of autoformalization. It's quite an old one. So this is not deep learning. This is probabilistic context-free grammars. So we take something which looks quite informal. It's not exactly Latex. It's sort of, but it's also not formal math. And we run it through a trained probabilistic context-free parser. The parser is trained on many examples of the informal thing coupled to the proper disambiguation, to the proper formal thing. And on top of that, when we get, like, because it's non-deterministic, when we get multiple parsers, we take the most plausible ones and we basically give them to the whole light hammer. And the whole light hammer looks at the whole light knowledge base and does the hammering thing and tries to prove those particular disambiguations or formalizations of these informal statements. So this is like I don't think we have a fully working autoformalization system working on some arbitrary Latex or whatever, but this is sort of a first step in that direction. Okay, so I'm done with the demos, and now the question is what I do in the next 10 minutes. Premise selection. I think I have said quite a bit about it. So yeah, these are the hammer systems made popular in Isabel. The success rate we could get some 5-6 years ago was 40 to 45%. The miracle which happened some 3-4 years ago is that Cezary Kališík and Lukáš Čajka could actually get a decent performance also on the Coq standard library, which is very distant from standard first order logic. So that was quite surprising to me and quite nice. And what I was showing now, is that we are getting to something like 60% on the Mizar dataset. Basically, thanks a lot to strong internal guidance of the automated theorem provers to sort of this enigma systems. So there is a lot to say about the various methods that people have used for premise selection. So the questions are, how do you characterize mathematical formulas, like by some symbols or by some more semantic features? What machine learning methods you use, like actually a simple distance-weighted k-nearest neighbor is a like baseline that is very hard to beat. But there are state-of-the-art methods like gradient-boosted decision trees or graph neural networks that are pretty competitive and typically improve on the simpler methods. Then it's interesting to apply like stateful, for example, neural methods like recurrent neural methods and transformers, which so all the previous methods sort of look at just the conjecture and the relevance of some formula or premise in the big knowledge base to the conjecture. What the stateful methods like recurrent neural networks can do is that when they propose the first premise, they change their state, and based on that, they recommend the next premise. So you can compare it to how recurrent neural networks are used to do machine translations. Like once you have decided to do the translation in some way, the recurrent neural network sort of ensures your internal consistency and grammatical consistency of the translated statement. So in this sense, these are relatively interesting methods to use, and we are getting quite interesting results from them. And what you obviously always can do in machine learning is to combine all the different methods. That's called the ensemble methods, and that typically also gives you additional performance. I will not go into this because that will so you can see how isolated this field was back in 2006, because I have boldly called it machine learning for automated reasoning. It's like what it does is this sort of infinite feedback loop between solving a large number of problems in some corpus, which are somehow related, and learning from the solution. So in this case, the machine learner was learning the premise selection task, how to choose the most relevant premises for proving the particular conjectures. And this game has been played over and over since then. So we have, for example, this ATP boost system by Bartosz Piotrowski. And these are some graphs showing you the sort of learning / proving loop on a particular smallish Mizar MPTP dataset, where in each round we basically increase the number of proved problems. And the red line is the k-nearest neighbor, and the better lines are these gradient boosted trees, these XGBoost methods. And these lines are growing sort of much more linearly than this sort of logarithmic growth, and they show you the number of proofs. So even if we cannot prove more theorems, we can still come up with alternative proofs. So that's quite interesting in this many iterations. And this is some histogram of the how many proofs we have for which theorems. Low-level guidance. So let me try to do at least that. So the simplest theorem prover I could think of, like some 10 years ago, was this LinkUp, which is a minimalistic tableau prover, which can be implemented in, I don't know, like the core algorithm is like, I don't know, 15 lines of prolog, and it constructs this tableau, which is basically a proof tree by some sort of extension and reduction steps. And so we have been trying to use this partially produced tree as a characterization of the proof state. And based on the proof state, we would advise which action, which of these clauses to apply to the proof state. So it's a very nice setting, because the proof state is quite compact, unlike in the sort of state-of-the-art big resolution superposition style provers. So we have tried several times. The first system was the machine learning connection prover. Then we did a fairly efficient one called female cop. And then some 3 years ago, we were impressed by the AlphaGo AlphaZero thing by DeepMind. And we have decided to do exactly what they did, like modulo the single player versus two players. And we put the Monte Carlo tree search into that. And also quite strong learners like these gradient boosted trees. And what we are doing is to, for the state to learn the policy, like which clause you should choose, and also the value of the state, like is the state going to lead to a proof? And that, I'll skip this, really, that was like first pretty good breakthrough in this internal guidance, because in something like 8 iterations, we could go from 5 iterations. We could go from something like 1100 proofs to something like 1600 proofs, which is a pretty big improvement in the theorem proving field. So so that was like a first sign that the methods are starting to work. And I would say we were encouraged by all sorts of people to do deep learning, but deep learning was so slow compared to the gradient boosted trees that we basically couldn't make it reasonably work in some reasonable time limits at that time. We sort of made it work later. So this sort of toy theorem prover has been used since for quite a lot of experiments by other people. So there is FLOP, which uses curriculum learning on basically a single proof, 1 times 1 equals 1, to learn like multiplication in the arithmetic domains, and that's very interesting. And then there are all these incarnations like PLCOP, the GNN COP, where we actually put the graph neural network into it, and it started to do something. Michael Rossen has a lazy COP, and Joel Zombor is trying to learn explainable prolog actions / tactics from the proof traces. So this is quite a nice environment for playing with a simple prover and combining it with machine and reinforcement learning. The biggest thing I already advertised, so it's this guidance of state-of-the-art automated theorem prover like eProver, which it doesn't have the notion of state like this simple tableau, but it has these 2 large heaps of clauses, the processed and unprocessed clauses. And you sort of have to do something with that. You have to decide what will you learn on. So what we learn on are the clauses used in the proof, and the negative examples are the clauses chosen by the theorem prover, which however weren't used in the proof. So these are some sort of hard negatives for you. And we, like Jan Jakubov is the main developer, with gradient boosted trees and very recently graph neural networks, efficient graph neural networks by Mirek Olshak, which are sort of logic oriented. So he, for example, hard codes negation, can really do quite nice iterations. So we have this 70% improvement where we, on the Mizar corpus, we start with 15,000 proofs, and in I don't know how many, 7 or what iterations of learning and proving we get from this 15,000 to the 25,000. I think I'm 2 minutes over time, Mike, so I should probably shut up.
Okay, I mean, if you have a conclusion slide, you can share that, but.
Oh yeah, so Martin Sura has done this recently for Vampire, so it's the ultimate automated theorem prover. Okay. I have already mentioned Tactic-To, so I can skip this. So this was also a demo. What I probably missed is this symbolic tasks done with neural networks. So it started with Bartosz Piotrowski when he basically learns normalization of polynomials or algebraic rewrite rules with recurrent neural networks and transformers. And you have probably all seen the follow-up work by Facebook on integration, etc. So that's quite interesting. Thibault Gauthier has a nice deep reinforcement learning toolkit for synthesis. So here I come back to the question in the beginning. So he synthesizes combinators for a given lambda expression or the Fontane equation for a given set. And the ultimate goal is to learn argument synthesis for tactical theorem proving. And Jelle Piepenbroek is going to submit a paper very soon where he really greatly improves the reinforcement learning in this setting. So this is basically a teaser. And then there is this whole conjecturing thing that sort of slightly exploded last year, where people basically started to use transformers, like I'm probably guilty of. So here is a sort of a bullshit proof generated by GPT-2, which was run forever on the Mizar library. And if you are not familiar with Mizar, you will probably believe. So this actually type checks. So it's a bullshit proof. You can, if you understand the semantics, you will see that the GPT-2 is doing totally wrong steps, but they look very convincing. So this has been taken up by, for example, OpenAI running these experiments on MetaMath, training a crazy big GPT, etc. And actually, we do sometimes generate interesting conjectures. So, for example, we generalized theorem about groups where the finiteness condition isn't needed, but we just couldn't prove it because it was too hard for the automation. So that's it. I will skip the autoformalization. Oh, there is no conclusion. Let me just show you that this is quite fun. So when you do neural network sort of autoformalization, in the sense that you have on one side Latex and on the other side formal math, in this case Mizar, this is what you can do. You can watch the predictions of the neural network as it is being trained. So this is the correct statement in Mizar, and this is the input Latex. And you can see that the output of the neural network, when it's not much trained, is total bullshit. But then already here, it focuses much better. And by snapshot 7000, it basically generates something that is alpha equivalent to the correct statement. It's equivalent up to the renaming of variables. So
how is it being trained?
Oh, so I took the full Mizar corpus, not just the top level theorems, but all the lines, which is something like 1 million lines. And there is a translator to LaTeX from that. So in some sense, the LaTeX is synthesized. So it's not through human written LaTeX, it's synthesized from the formal text. And that gave me 1 million training examples on which I just ran some standard Google NMT toolkit, neural machine translation toolkit, which was basically used for training English to Vietnamese or English to French. And that's it. I mean, I didn't train it. My PhD student, Sean Wang, trained it. What was also quite interesting in this experiment, so Sean was sort of learning on that. And we found out that what really made a lot of difference in these tasks is a mechanism called attention, which you probably, some of you at least, have heard about. So the performance of the recurrent neural network without attention was quite a bit worse than the performance of the neural networks with attention on these tasks. So this is just a teaser for you to show you that it's not completely hopeless like some people believed like 5-10 years ago. And even if the recurrent machine neural network or some other machine learner doesn't get it perfectly, quite often you can do something with it. So I think sort of the path to autoformalization is a pretty interesting thing to pursue today. So that could be the conclusion. Here are some acknowledgements to all sorts of people who are today working on that, and some references. And here is my advertisement. So this year, we actually managed to have some hybrid AITP in Oslo, and you are cordially invited to come next September to Oslo, or at least participate remotely on this conference/workshop, which is pretty informal and discussion oriented, called Artificial Intelligence and Theorem Proving. Thanks for your attention.
Thanks, Josef. We'll take questions from the audience.
Yeah, can you explain the type system that you used in the
type system?
Do you mean some? So there are various type systems for various interactive theorem provers.
Well, in any of those examples, you had a lot of demonstrations from GitHub. So what is the type system in there?
In the MISAR examples, you mean things like
yeah,
this?
for example, here, yeah.
Okay. So that's an invention of the MISAR people. It's called a soft typing system. So from the point of view of the sort of foundational type systems, it's actually not a type system. It's basically a way of treating first order predicates and providing automation for that. So basically every MISAR type, like for example, prime, is a predicate, and what you actually this is not a good example. Let me try net here. Yeah, so net is an actual number, and it's a predicate saying that A is a natural if it is in omega. And so you can, when you are translating to first order logic, you can very easily expand all MISAR types to first order predicates. Well, what MISAR does for you automatically are these type inferences that are called registrations in MISAR. So for example, here you register the fact that omega is a non-empty ordinal. So whenever MISAR sees the symbol or function omega, it will automatically derive the predicate non-empty and predicate ordinal about it. So you have a lot of these typing hierarchies. In some systems, like for example in Isabelle, there is a related system called type classes. So it's also not like a foundational type system, but it's something on top of the foundational system that basically propagates the predicates that hold about your object automatically.
Christian, your hand is up. Would you like to?
Yes, sorry. Let me just try to. Yeah. Okay, so I just have a meta question on. So let's say if you could pick one, like ITP or system like MISAR or HOL or whatever to do autoformalization, what would be your first choice?
So I made a choice 20 years ago because MISAR was sort of very friendly to me as a guy who only knew first order logic and set theory. And it was also designed by a linguist, like Andrei Tribules, among other things, was a linguist who had really a lot of focus on these readable proofs. So I think some 9 years ago, I was completely surprised. I was organizing a workshop on mathematical wikis in Nijmegen, collocated with the ITP conference. And I have invited the guy behind the proof wiki, and it looked like he totally independently arrived, even though proof wiki is sort of informal, at a very similar proof style, like the MISAR guys. So for the autoformalization, one of the things I was sort of nudging my PhD students to do was to go between ProofWiki and Mizar. And I actually even had one researcher working for me who was a Mizar guy, and he was aligning the proofs between ProofWiki and Mizar. So in some sense, I do have a corpus of informal and math in ProofWiki aligned with Mizar to some extent. What I would also, so we have also played with FlySpec quite a bit, but there it sort of probably works on the level of formulas, because you, like Tom Hales has been quite nice in explaining how the FlySpec informal proofs correspond to the formal proofs. But the tactical proofs are sort of unusable and unreadable for humans. So that's a big negative. So I would like, I already did basically chose Mizar for that, but I would say any system with declarative proofs, like Isabel, for example, has a big archive of formal proofs. And so some of it is not declarative, some of it uses sort of the old technical language, but a lot of it is sort of written in this sort of Mizar declarative proof style. And I believe there are even books that has been formalized by the Isabel people. And I haven't looked at the proofs, but I would bet that there might be interesting parts of the formal proofs that reasonably correspond to some books. So that might be one thing to look at. On the other hand, like, so we have done, I didn't have time to go into it. We have done also experiments with unsupervised machine learning, which is sort of the next big thing in machine translation. And since I have seen it, so this was like 2 years ago, I sort of started to believe that we actually don't need so much aligned corpora for this task. So I think I'm happy that we did the sort of experiments on the big sort of aligned corpus generated from Mizar, even though it's synthetic. But I think the future is really bright in the sense that we will not need too much aligned corpora for this.
Just as a thanks. Just as a general question, I mean, each of your experiments, of course, you have to work with a particular system. So you did quite a bit with Mizar, and you discussed some results with other systems. And then how much work would it be to repeat an experiment? Say, for example, we have this big lean math lib, and we wanted to do a comparable exercise.
I think it's become sort of routine. Like, so ever since Joe Hurt and Larry Paulson and his collaborators did the sort of hammered translation for Hall and Isabel, and then Lukáš Čajka and Cezary Kališik did the hammered translation for Kok, I think, and ever since like Thibault, so the work on tactical, like to do it right, to really make it work, the engineering issues with the tactical guidance are really, it looks simple on one slide, but it's 2 years of Thibault's PhD work. And the same for the tactician, for Lasse Blaubruk's works for Kok. So if you are talking about the hammer systems, it's probably not so hard to do some translation for lean, following, for example, what has been done for Kok. If you are talking about the tactical systems, then it really depends on the design of the internal levels of the system, like how friendly it is to do something like Tacticto and Tactician are doing. You may get in trouble. So, for example, Lasse got in trouble with some monad inside Kok, and it took him a while, and it's still not completely solved, and he may need some collaboration from the Kok developers to improve on that. But I would say the advantage of lean is that, at least my impression is that it's still a system which is very much in development, and Leo Moura isn't afraid to completely change everything from version 2 to version 3 or whatever it is. So I think if you get reasonable support from the developers to do something like tactical, then that would be what I would try to do. And at least what I hear is that they are having the sort of meta programming framework there, which might be something to look at. But I'm not really a lean expert, so yeah.
Here's a really very open question for you, which then maybe I don't know what kind of answer one could give at this point. So one, especially with AlphaGo and AlphaZero, one had this seeming quantum leap in the capabilities of machine learning and AI. And so is it just a matter of unpredictable time before we see a similar quantum leap for AI and theorem proving, or is AI and theorem proving obviously harder in some way we can pin down, or do we have any idea?
Yeah, I would like to know. So you could probably sense that I got myself. So what is really nice is that sometimes you really get surprised by these tools. So for example, with Enigma, we were getting some improvements, like 10% or whatever. But then one day we simply trained it like hell, and we ran several iterations on enough data, and it gave us this crazy 70% improvement.
And does the question of what improved, what was the improvement, can that question have any answer? So this specific case.
So I would say it was a combination of a good and fast machine learner. The fact that it was fast meant that we really can do a lot of these proving / learning loops, and that gives us a lot of data to learn from, and that seems to be important. So for example, after that, my PhD student Zargartzel did an experiment with completely stupid e-prover. He totally removed all heuristics which the theorem proving people have been inventing for many years, and he just trained it. He just overtrained it, and he made it better than the best human written heuristic just by the machine learning. So this is a partial answer. Well, these are two partial answers to the question. Like one is that this is sort of behaving quite unpredictably, like some things don't work for a long time and then suddenly you make them work. And the other answer is that there is this sort of AlphaGo, AlphaZero approach where you just sort of do some of these iterations, and you are hoping that you will gradually reach bigger and bigger proofs, and you will learn whatever the human might think about, or the neural network will generalize so well that it will even generalize to unseen cases. And it's doing something. It's definitely helped, but I think that the problem, even with AlphaGo, AlphaZero, is that basically it doesn't transfer. So if you give the trained network a Go board which is twice as big, it will be stupid. So a lot of also the transformer-based results. For example, we, like Bartosz Piotrowski, got a bit annoyed by the Facebook people, so sort of scooping him when they did this integration. So he looked at their data set, and he saw that the training data are extremely saturated, and the testing data set is sort of, after some modifications, very similar to what is in the training data. So in a lot of these methods, you see a lot of memorization and very limited algorithmic learning. So for example, the inductive logic programming, which I was doing my master's thesis, is really about learning explainable algorithms and non-trivial algorithms. And I don't see the current neural architectures to do that. So for example, if you are a mathematician, you can eventually come up with something like Gaussian elimination. And there is no way for the current architectures to come up with such non-trivial algorithms. So I think I totally believe that the OpenAI and Facebook people will saturate their data sets to the level that they will be claiming that we have reached some grandmaster level in mathematics. But I think we need sort of more advanced algorithmic learning to really do the things that the mathematicians are doing. The saturation by a lot of data will definitely give us something, and it already is fairly useful. Like I can prove whatever, some version of Carmichael's theorem. I can prove very long theorems in Mizar. So it's really useful, and the humans aren't so good, right? Like, let's face it. But for a lot of mathematics is invention of algorithms, and I don't think of non-trivial algorithms, non-continuous algorithms. So it's even questionable how much the continuous optimization methods can take us there, like how much we don't have to do some, let's say, evolutionary methods, for example.
Let me throw out another general question. I mean, if I sit back and I think it's fair to say your talk is computer science and not mathematics. It's definitely methods, and one's learning a lot and making great advances. But are there points in your work where you wish you could imagine ways that mathematicians could contribute? So for example, one obvious answer is yes, they can continue to develop these libraries of formal mathematics that can serve as training data. But are there other ways?
Yeah, good question. How could mathematicians contribute? So one thing. So for example, Tom Hales has this formal abstract project, which is quite a bit what you just mentioned, right? But it's not asking the mathematicians to fully write the proofs. It's just asking them to try to formalize the statements or abstracts in Lean, and then already that would be pretty useful. And I think not just for our research, it would also be useful for mathematicians because it would allow them to search semantically and do things like that. So that's one very clear point, and everybody should join Tom in writing formal abstracts. What Tim Gowers gave a nice talk 3.5 years ago at the Big Proof conference in Cambridge, where he was sort of showing on an example from IMO, from the Mathematical Olympics, how he's sort of following his nose and doing some things and not doing some things. And I think he made a statement which I disagreed with, which was like, I can get a programmer to program these things, and I said, well, you cannot. This approach has failed long time ago, and I'm not sure if I convinced him. But yeah, the argument is that you need some automated learning, at least that's what I believe in, that you sort of shouldn't be programming these things explicitly, but training systems that learn those rules. But what he was showing was very instructive, and there were high-level explanations of what he was showing. So I guess we may be able to learn from such things in the future. And what is maybe also pretty useful are these things like the stacks project, which are also sort of going in the direction of some semi-formalization, which makes it easy for us to try to detect the definitions, for example, or the references. So maybe one request to mathematicians is don't write crazy LaTeX. Try to, like, for example, the stacks format is really nice for the computer scientists to process and to do autoformalization experiments on that much more like than on the full archive corpus. But like this idea of coming up basically of this high temperature to low temperature, where we would have some tool chain or some series of levels which we could gradually attack, sounds quite interesting, and something that where the mathematicians could help, right? Like ideally, like they would, for example, be interacting with some learning and proving system where they would say something sort of minimalistic that they are telling to the student, and then well, maybe the system is too low level for that. Well, then the mathematician would explain in the more low level language, and at the same time try to explain what he meant by the high level concept or trick or method, right? So I can imagine that the methods will come that will also be capable of learning in this way, in this sort of explain me the math and I do not understand what you are saying. So that's probably pretty vague at the moment.
Okay, but it's an inspiring idea. More questions from the audience? Or?
Excuse me. So do you think it's possible to map a Mizar type system to the types that are used on archive papers, for example, in algebra?
For example, what? I cannot hear you.
We can't hear you.
I don't know what would be the type system for archive.
You're muted, Stan. Stan, or okay. No. Okay. I don't know. I mean. More questions, or we'll have several more talks on this topic, and so it'll be interesting to perhaps come back and discuss. You know, these are very open-ended questions. But let's thank Josef for a very enlightening survey and a lot of interesting work. And so next week we'll be having Christian Zegedy, who will speak about language models as mathematical models and at the same time. So I look forward to seeing you all then. Thanks, everybody.
Thank you. Bye-bye.
Thank you, Josef.